So, you want to learn how to integrate by parts, but why would it even be necessary? Could the types of integration we've learned up until this point be used instead? Well, let's see with a few warm-up problems. Okay, so to integrate x squared, we can just use the standard rules of integration to get x to the third over 3 plus c. It's the same for the next one. If you want the solution, it's 10x to the third minus 6x squared plus 2x plus c. Alright, so what about this one? The integral of x cos x dx. Well, let's try to use u substitution first. Let's set u to cos x and solve. So we get du is negative sine x dx, which means that dx is negative 1 over sine x. Normally, the next step would be to plug back in, but negative 1 over sine x won't cancel out with any of the original terms. If that's the case, we'll need to solve by integrating by parts. There are two methods for integrating by parts. First, let's go over tabular integration, which in case you couldn't tell, uses a table. Before setting up the table, we need to separate our base equation into two parts. One that can be differentiated easily and eventually yield 0, and the other that can be integrated multiple times. Once that's decided, we can set up the table. The table uses 3 columns, one for the sign, one for the derivative, and the last for the integral. Please note that the sign will always alternate between positive and negative. Now that the table is ready, put each part of the separated equation into the corresponding spot in the first open row. From there, find the derivative or integrate until the d over dx column reaches 0. Once that happens, all we need to do is take the answer from the table. We do this by taking the sign and the derivative from the first row and the integration from the next row down. This is repeated for the entire table. It may seem complicated, but it'll become much easier after a few problems. Let's start by finding the integration of x cos x dx. So first we separate the given equation into two parts. We can take the derivative of x and it will eventually become 0, so we'll use that for our d over dx. That just leaves cos x for the integration. Now we plug the values into the table. For d over dx we have x, 1, and 0, and for the integration we have cos x, sin x, and negative cos x. And finally we analyze the table to find the answer of x sin x plus cos x plus c. Before we move on, let's try one more. This time we'll integrate x to the fourth times e to the negative x dx. While this integration might seem more complicated, it actually follows the same process. For d over dx we'll use x to the fourth, and for the integration we'll use e to the negative x. We then plug those numbers into the table until x to the fourth becomes 0, and then just follow the same process as before to get the answer of negative x to the fourth times e to the negative x minus 4x to the third times e to the negative x minus 12x squared times e to the negative x minus 24x e to the negative x minus 24e to the negative x plus c. Alright, so now it's time for the other method for integrating by parts. This involves following the equation of the integral of u dv equals uv minus the integral of v du, where u is a part of the original function found by following a set of rules known as LIATE, or LIAT. This stands for logarithmic, inverse trig, algebraic, trig, and exponential. This leaves dv as the other part of the function. From there, you would solve by plugging in for uv minus the integral of v du using calculus when necessary. Since the integral of u dv is what we're solving for, it can be ignored unless we need to integrate by parts more than once to find the answer. But why would you use this method instead of the tabular method? Well, sometimes it isn't practical or even possible to use a tabular method easily. Take the integral of e to the x cos x dx. There is no easy way to split this equation up so that the derivative would eventually equal 0. Anyways, let's get to some practice problems. First, we'll try integrating x squared ln x dx. So let's start by choosing the u. Following LIAT, we should set u to ln x, as it is a logarithmic function. That leaves x squared as dv. Integrating, we find that v is x to the third over 3, and the derivative of ln x is 1 over x. Then we write out the equation the integral of u dv equals uv minus the integral of v du, and plug in and solve for uv minus the integral of v du. Simplifying the integral, we get the final answer of 1/3 x to the third times ln x minus x to the third over 9 plus c. Next, we can try integrating e to the x cos 6x dx. Honestly, compared to the last one, this one will take much longer. Why? Well, you'll see soon enough. Like before, let's start by applying Lyot. Since cos 6x is a trig function and e to the x is exponential, we'll use cos 6x for u and e to the x for dv. We need to integrate dv to find v, which is 1/5 e to the 5x. Then we can find the derivative of u, which is negative 6 sine 6x. Next, we apply the integral of u dv equals uv minus the integral of v du to get 1/5 e to the 5x cos 6x plus 6/5 times the integral of e to the 5x sine 6x dx. From here, we can't actually integrate without using integration by parts again, since none of the terms will cancel out with u substitution. So that's exactly what we're going to do. Going through the same process as before with the new integration, we set u to sine 6x and dv to e to the 5x. This gives us 6 cos 6x and 1/5 e to the 5x when we derive and integrate respectively. Then we use the integral of u dv equals uv minus the integral of v du again, plugging uv minus the integral of v du back into the source integral in order to find the answer. You'll soon notice that the integral, again, is not able to be simplified. Well, that's because we haven't plugged back in the integral of u dv, the beginning part of our equation. If we do that, we're able to simplify the integral and get an answer of 25 over 61 times the quantity of 1/5 e to the 5x times cos 6x plus 6/25 e to the 5x sine 6x. And that's a quick introduction to integrating by parts.